As Pat mentioned, I'm Yip-Hoi, and our project, again, is getting back into composites, but this time looking at a secondary process, machining. How do we machine a specific type of composite product, which is honeycomb sandwich panels? Before I get into the details, let me just introduce our team first. So there's Dr. David Gill, who couldn't be here today. His specialty is in machining, tooling, CNC, computer-aided manufacturing. There's myself, and I'm a CAD geometric modeling guy. Our team had 5 manufacturing engineering students, all of whom are seniors now, ready to graduate, getting excited to graduate in a few weeks. And our industrial partner was Safran. Kirk Dessler, Eric Westberg, and Ryan Vanderveen worked with us extensively over the year on this project. By the way, Safran at the time when we got the grant was called, most of you know, Zodiac Aerospace. The company up in Bellingham, the division in Bellingham, was referred to as Zodiac Aircraft Interiors. So that was their name at that time. So that kind of leads me into the problem. The product that we were focusing on is your aircraft interior product. And most of us are familiar, of course, with those pesky aircraft overhead bins that cause us frustration and stress when we're waiting to get onto the aircraft, wondering if our bag's going to fit in there or if there's even going to be room for it. But also, there's much more than that. There's the aircraft interior lining, but there are also the monument structures, such as the galley area, the lavatory areas, and the bulkheads that separate the various parts of the cabin. And these products, they are made, I guess the best analogy I can use is, how many of you have ever built a piece of IKEA furniture? Raise your hands. Come on, there are more of you than that, I think. Don't be shy, don't be ashamed. We've all done it. So that's kind of the same idea, except that the shapes that are cut are a lot more interesting. And they are both bonded and fastened together. Also, too, the material, of course, is very different. The material that's used is a honeycomb structure that is built from aramid fibers that's dipped in a phenolic, and then there are face sheets that are bonded on either side. So in order to get that product into the interesting shapes that you have in the aircraft interior, you have to cut it on a large router, a 5-ax router, which is basically a high-speed tool that cuts the shape that you want. And then these are assembled together. So that's basically the product. The challenge that Zodiac or Safran encountered was that this material doesn't cut very well. And as you can see here on the picture in the middle there, what is referred to as flagging and fraying takes place. So there's a lot of parts of the honeycomb that stick out, and the face sheet doesn't cut well. There are fibers that stick out there too. And this is because the skin and core are very different material. It's an anisotropic material, and it's also very compliant. So you put a load on it, and it starts to vibrate. So unlike a metal, it has a lot of challenges to cut. So the project that we came up with was to utilize high-speed videography and modeling to try and study this problem. We thought about other traditional methods of looking at cutting. We felt that none of those would work. Things like looking at cutting forces, thermography, acoustic noise. Maybe at some point in time we can look at those techniques, but we decided to simplify and say, let's just look at it first and see what's going on. And that in itself is not easy because of the speed of the cutter. It runs 15,000 to 20,000 RPM. You have a lot of dust, a lot of vibration, so you really need to have high-speed video to be able to capture that effect. So that's our problem, and well, JCATI was really very helpful to help us do this. First of all, it helped us acquire the high-speed video cameras that we used and allowed us to look at machining at 20,000 frames per second. Bet said not to have any videos, so I can tell you we have a very nice a website with videos if you're interested in looking at these. We also spend a lot of time modeling, and the funding was helpful to support the students who did all this interesting work in modeling the cutting tool, modeling the structures that were generated to help us understand how the cutter interacts with the structure a bit better. And then probably the biggest thing that it helped was to help us establish an interaction framework with our sponsor. So we were able to really work with them very closely and collaboratively to be able to study this problem, and we were really happy about that. So just a few insights from the research that we came up with. Those of you who are familiar with machining understand that if you cut a slot, the top of the cutter is referred to as the climb side, and the conventional side, and the bottom is referred to the climb side. And the machining metals, the conventional side produces the worst result in terms of quality and finish. We found when we did some testing that the opposite was true when we cut these composite sandwich panels. The climb side, as you can see from the photo there, you have all this flagging that's taking place, which, by the way, I should have mentioned previously, you have to remove this before you can assemble. So the Safran spends a lot of time with manual reworking of the panels before they can actually start assembling together, and it's very time-intensive and costly for them. So we found that this was one issue that was actually the opposite, that actually the conventional side is a better side when cut, which means that you have to cut clockwise around the panels to produce a better result. The picture over there shows one of our students, Georgia, and she's actually at Safran working on one of their production machines doing testing. So that, again, highlights the type of relationship we were able to develop over the year to be able to actually go into a production facility and set up an experiment on their equipment. And we're very grateful for them to allow us to do that. Great experience for the students, by the way, too, to actually go in and work on production equipment. Another insight we had, too, is based on the type of cutters. We found very quickly that Safran uses a lot of different types of cutters, not just at the Bellingham facility, but at their other facilities where they machine, too. And what we found was that certain cutters have better performance than others and can give you a better cut. So one of the properties we looked at was the rake angle. And if you want to think of the rake angle, it's really the sharpness of the tool. So tools that are sharper, such as the one here on the right, which has a higher positive rake angle, tended to cut better than ones which had more blunt edge. And this is helping the process planners pick the best cutters. So this information is very useful from that point of view. So this was another important insight that we came up with. And then a final one, too, we looked at actually the tilting the cutter into the direction of feed to see if that improved the cut. And we did find that that did help quite a bit, depending on the cutter you used. We found that, for example, if you tilted 25 degrees, you got a slightly better cut where the flags were a lot shorter. And again, that reduced the amount of rework that was necessary. So again, with a 5-axis machine, which all their routers are, they can actually do that tilting in the direction of the feed, although it's limited in some ways because you can't do every single shape with it. It's still something that can be applied in certain circumstances. So these are 3 interesting insights that we came up with from the research. Moving ahead to talk about the ripple effect, during our discussions during the time of the project, we had a lot of back and forth about different things we could be doing for the future. And one of the things that, one of the things that we talked a lot about is another problem which deals with the assembly of these panels, which requires inserts to be bonded into the panel. And the problem with that is that it's very manually intensive. So once you machine a hole or a pocket in the panel, you have to the workers manually insert this insert, and then they have to inject glue around it so that it bonds to the panel. And the problem with that is it takes from 1 minute to 2 minutes for that per insert. And some of the large panels have from up to 50 to maybe even as much as 75 inserts in them. So there's a lot of time involved. And it's also takes up a lot of a footprint in the factory because each of these panels, some of them can be very large too. So we came up with this idea in talking to the engineers about trying to automate this by integrating this process onto the routers. So in other words, design a robotic end effector that places the inserts after the pocket is cut, and then inserting the glue around it and having those inserts bond in before the panel is taken off the router. And from those discussions, this year we were able to get going 3 integrated senior projects for our students involving 8 majors to actually try and solve this problem. So Safran is really excited about this, the group that we're working with, as well as the students who are kind of working now towards the first prototype, which will be due at the end of the term. A couple of other things that we did too is we started looking at another type of honeycomb structure, which is aluminum. We actually picked the more difficult material to start off with, the composite material, because of the different properties. But we're thinking that we can learn a lot by looking at the aluminum panel too, and correlating the results, trying to understand really what the mechanics is that's happening. So, and again, Safran is helping us a lot by providing us with materials to help study the cutting effect on aluminum. We've also spent a lot of time reverse engineering cutting tools. Because if you look at the vast range of cutting tools out there, they come in very different sizes and shapes. And the manufacturers don't give you information about them because it's their proprietary shape. So we're using photogrammetry to try and reverse engineer cutting tools so that we understand better what their properties are and how they impact the cutting that's taking place. And then finally, we're still not done with that problem that we started with. We're still moving ahead and looking at it in more detail. Safran is providing us with materials up there on the left. Here you can see that they've created a special type of panel for us where they're using a translucent face sheet so that we can actually see through this face sheet to see what's happening when the cutter interacts with the material. So they're actually helping us with materials that they don't normally produce to help understand the problem better. And we're also looking at tilting the cutter so that it undercuts the face sheet. And they can do this again because they have machines where the head tilts. And that's a way to undercut and maybe remove some of the flagging to help with the assembly. So these are some ripple effects that we're excited about. We have projects that are going on, the senior project, and we have students that will be working on these, for the foreseeable future. And then just to mention that there is, academic production. I know this is not supposed to be an academic talk, but just to point out that, we have published at ASME, and we also have one that we have to present in a few, not too long off in June, at NAMRAC on this work. And none of this would be possible without the JCATI grant that we've gotten. So in conclusion, we feel this was a very successful collaboration with our industry partner that has yielded some very valuable insights into the machining of Honeycomb sandwich panel. Really and truly, to me, the big thing that came out of this was the strong working relationship that we now have with the process planning group at Safran's Bellingham facility. And this new senior project that we talked about is one good example of something that would not have happened or not be happening if it weren't for the funding that JCATI provided. And we see additional projects in the years to come. We're already in the process of talking about projects that would not, again, be possible if we hadn't had this collaboration through the funding provided. So we are very happy and thankful for the funding that was given to us. Thank you.